Hey everyone, this is Dr. Walker. This is the second guided example from video 560, but it's really about a discharging capacitor circuit. Now that we've talked about the time constant, we're able to do this problem. We have a capacitor being discharged through a resistor, so the switch is at position B. We don't have the battery as part of the circuit here, so we have a fully charged capacitor and is going to discharge through that resistor. The first part says, after how many time constants is the charge on the capacitor 1/4 its initial value? What's important to understand here is what the question is asking. A lot of time, when people see time constants, they're thinking, oh, the problem is asking about time constant. But the question is not asking for the time constant. The question is asking, well, how long does it take for the charge to become 1/4 of its initial value? And however long it takes, just write that answer in terms of the time constant. So the question is asking for time. Remember that time constant is a unit for time. So that being said, let's look at part A. We know that we want to use the equation for charge on a capacitor for a discharging capacitor, and that is that the charge as a function of time is equal to the maximum charge times e to negative t over tau. And we're also given that we want the charge to be 1/4 of its initial value. We know that initially it has its max value. So we want this charge to be the maximum value divided by 4. And we want to see, well, at what time do we get that amount of charge? So we have Q max e to negative t over tau. And now we can take the log of both sides. So let me just move that a little bit here. Take the, we can divide out the Q max to get 1/4 here. And now we can take the log of both sides to get rid of the exponent here. Take the log of that. And we're going to get log of 1/4 on the left. And then we're going to get negative t over tau on the right-hand side. And now we just need to solve for time. So time, we're going to divide by -1, multiply by tau, negative log of 1/4 multiplied by tau. We plug negative log of 1/4 in the calculator, and that's going to equal 1.39, and then we have the tau. So there we have it. Our answer for how long it takes is in terms of the time constant. We can visualize it to make sure it makes sense. We know that the charge on a capacitor looks like this. And we know that over here it's about 3 time constants if we look at our previous graphs. So after 1.39 times constants, we're about a little bit less than halfway. So after this amount of time has passed, right, this is charge as a function of time, how much charge do we have left? Well, we have about 1/4 of what we initially have. So that's part A, and now let's look at part B. Let's go ahead and use red for that. This one is asking, after how many time constants is the stored energy 1/4 of its initial value? So it's going to be a very similar process. And we need energy as a function of time. Now we know that energy does depend on charge, so we can write energy as the charge squared over 2c. That's one of our expressions for energy. That way we can use our definition of how charge varies as a function of time, because we know the capacitance does not vary as a function of time. So we're going to get Q max e to the negative t over tau, and we're going to square that for the charge. And then we're going to divide by 2c, and we just need to simplify a little bit. So the squared goes to the Q max here, and then the squared goes here in the exponent, e to negative 2t over tau. This is all over 2c. So this is an expression for the charge, the energy as a function of time. And now we want the energy to be 1/4 of its initial value. So we want this energy here to be 1/4 of the initial value, and then figure out at what time does this happen. So we want this right here to be equal to 1/4 of its initial value. And the initial value for the energy is going to have not Q, but it's going to have Q max, right? Because initially you have maximum charge on a discharging capacitor. So this right here is 1/4 of the initial energy, and then this over here is the energy as a function of time. So we set them equal to each other, and then we're trying to solve for time, which is lowercase t. And luckily, a lot of this stuff cancels out. So let's take a look at what cancels out. The Qmax squared cancels out, and the 2c cancels out. So we're left with 1/4 is equal to e to the negative 2t over tau. And now we can take the log of both sides to get rid of that exponent. And so we're going to have log of 1/4 is equal to negative 2t over tau. And then once again, we need to solve for time. So we're going to divide by negative 2 and multiply by tau. We're going to get negative 1/2 log of 1/4 and multiply by tau. Plug this in the calculator. It's going to give us 0.693, and once again, it's in terms of the time constant. So at this time, which is less than one time constant has passed, we will have 1/4 of our initial energy.